Let's see if you remember anything from last time. If I want to find out, so a return that tells me how much extra I can consume, what am I looking at? Total dollar returns or total percentage returns? Yeah, total dollar returns. Tells me how much extra I can consume. Mr. Osawabu, you are late. For shame. He's done so well so far. Maybe it's just the rain. Is it just the rain, Mr. Osawabu? No, it's not. You could have taken the easy out. I applaud your honesty. Okay. Where are we? Oh! So, if we want to know, however, how our investment performs versus the amount that we initially put in, what are we looking at? Total dollar returns or total percentage returns? Total percentage returns, right? What are the two things that we have to add together to get total percentage return for stocks? Dividend yield and capital gains yield. Very good. What is the mathematical measure we use for variance, or sorry, for volatility or risk?
Variance.
Oh, I messed with you. Standard deviation. Mr. Bowrichter, why do we use standard deviation?
Variance can't be displayed as a percent, right?
Variance is percent squared.
Okay.
And so there's two reasons. Number one, standard deviation is in units we understand, same units as return. And number two is that it goes into the normal distribution, which we'll get to today. Let's see. Ms. Perry, what is risk premium?
Isn't it it's the difference between your risk and the risk-free rate?
Oh, you're getting close.
Risk-free percentage or something?
Let's just stop right there. Ms. Avila.
Is it the return minus the risk-free rate?
Yeah, it's a return on whatever the thing is minus the risk-free rate. Yeah, oh yeah, you had the second part, beautiful. Okay, so remember that any return you get over and above the risk-free rate is a premium for bearing risk. And so we call that the risk premium. And we can have a risk premium on bonds, we can have it on stocks, we can have it on the whole market. And when we get to chapter 11, we'll talk about the market risk premium. Okay, now let's see here. When we got to this part of calculating the sample standard deviation, did we work down or across? Across. And what was our procedure here? We go and we work across, and then when I get to the last step there, what do I do with my calculator? Store 1. And then I do that, all 4 of them. In this case, there's only 4. Sometimes you'll have more, sometimes you'll have less. Hopefully on the exam, you'll have less. Very good. Okay, and then once we get all those together, how do I get the sum of the squared deviations? What calculator motions would I do? Recall 1 plus recall 2 plus recall 3 plus recall 4. And that gives me SSD, or sum of squared deviations. How do I get variance from sum of squared deviations?
Divided by the degrees of freedom.
Divided by the degrees of freedom. And degrees of freedom, none of us know what it means, but how do you calculate it?
N minus 1.
N minus 1, where N is what, Ms. Menace?
The number of periods.
Yeah, it's the sample size, right? Okay. And so here we're going to be dividing by 3. Now we've got one more step here, and that is we want to turn variance into standard deviation. How do we do that? Square root. Very good. Thank you. Okay. Now, I told you that this time I would show you an easier way to do this. Would you like to see an easier way? Get your calculator out. Get your calculator out. Get your calculator out. As soon as you guys all have your calculators out, we'll get going here. Okay, now here's what I want you to do. I want you to look above the number 8. What does it say?
Stat.
Stat. And look above the number 7. What does it say? Data or data, depending on who you are and where you're from. So, it doesn't matter. By the way, did you know that data is plural? So you don't ever say, give me that data. You say, give me those data. Don't worry about it. No one listens. Right. Okay. So what would the individual be? datum. Datum, I think. I think it's a datum, yeah. Okay, so back to the story. Why are we caring about these two numbers? Because we're going to put these numbers into data, and then we're going to use the stat to calculate our statistics. So here we go. First thing I'm going to do is go to second and the number 7. Now, you will be tempted to just start entering stuff. Don't do it. And here's why. If our last problem had 5 data points, then after we entered 4, that last one would still be hanging out there, because remember, the calculator is like a wife. Mr. Bowrichter, why is the calculator like a wife?
So never forget.
It never forgets. That stuff is out there till the end of time. By the way, guys, how do you avoid this problem with wife? Don't do stupid stuff, right? Okay, so back to the story. What I'm going to do to clear this out, watch very carefully here. I'm going to hit second and then clear. What does it say above the CE over C key? Clear work. We're clearing out that entire worksheet. So now we know that it's empty. So here we go. We're going to start typing things in. 0.137. Now I want you to notice up here it says enter. I've got to enter that or it doesn't remember it. So there we go. And how do I know that it remembers it? Do you see the equal sign? Okay. Now I'm going to arrow down. Now we've got Y01. By the way, your calculator is set up to deal with 2 series of data at the same time. We're only working with 1. So we're going to totally ignore the Y's. Hit your arrow down. What do you think I should put in for X02? 0.358. Enter. Arrow down. Arrow down. What's X03? 0.451514. Enter. Arrow down. Arrow down. What is X4? 0.0888. Negative. Too bad we can't do it the other way, but here we go. Enter. Now I'm going to go through and make sure I got all my numbers in there right. How do I do that? I just arrow up, make sure they're all there, because the most common mistake would be to not hit enter and it just leaves it unchanged. So don't do that. So now that we have all the data in, we can hit second and stat. And up here at the top, it says Lin. And I used to have a lot of Chinese students, and at least one of them would be named Lin, and they would say, it's talking to me personally. And I'd say, no, it's short for linear something or other. I don't know. But just ignore that. Just know that it's done its magic. And now, do you see up here, it says arrows up and down. So that's what we're going to do. We're going to arrow down, and we see it says n is equal to 4. By the way, do you see the asterisk up there, the star? That means, yeah, this is the number the machine came up with. Okay, yeah, does that sound right?
Yes.
Okay, if it says 5 at this point, what do you know that you've done or forgot to do? Clear things out, right? Okay, arrow down. X bar is equal to 0.2144. What do you think X bar means? Yeah, it's the arithmetic mean, and the bar always means average in statistics. Okay, so now we've got those 2 pieces of information. Everything looks good so far, and I'm going to hit down again. And now I have S sub x is equal to 0.214323407. Now, S sub x is sample standard deviation. Sigma sub x is population standard deviation. Which one did we say we are looking for? Yeah, it's a sample. We only have a sample of this data. So, and by the way, in this class, for chapter 10 purposes, it will always be sample standard deviation. And when you get out in the real world and you start doing this, you're going to do sample standard deviation. And the reason is we don't know the whole population. We just never do in the real world. Okay, now let me ask you this question right now. If you wanted to find the variance of this thing so we can compare to what's on the screen up there, what would you do? Yeah, we're just going to square it. So let's go ahead and do that. There you go. Does that number look familiar?
Yes.
Yeah, very much so. It's the same thing. Now, was it easier to go this way or to do the pick and blowtorch method?
This way.
Yeah, this way is far easier. Now, good news is, yes, you can use this on the exam, and I hope you remember to. The bad news is, for the Chapter 11 problems, we have to revert back to pick and blowtorch, so don't get too comfortable yet. So, you say, wait a minute, I want to know that S sub x again. What I can do is go arrow up, and then arrow back down, and there it is right again, and now I know that it is because it's got the equal sign. When I had the square, notice the equal sign goes away. Does that make sense? Okay, now I'm going to show you something. So when I was a little kid, my mom says, don't touch the stove because it's what? Hot. What do you think I did? I touched it anyway. I'm like, what do you think I learned?
It's hot.
It's hot. Plus I don't have fingerprints on these two fingers. Now, back to this. I'm kidding, I've got fingerprints. Back to the story. So, I'm going to show you something here. I'm going to tell you not to do that, not to touch it, not to mess with it, but undoubtedly one or two of you will, but here we go. Sigma sub x. Some of you are going to just keep going, and then you're going to see this and you're going to like, aha, that's the standard deviation. Here's what you need to know. That is the population standard deviation. That is not something, this calculator image right here is not something we will ever use in this class. So don't go that far down. All you need to look at are n, x bar, and s sub x. That's it. That is it. And now, by the way, we have enough information to create the normal distribution, because for normal distribution, all we need are mean and standard deviation. Would anybody like to see me do that one more time?
Yes.
Oh, very good. Thank you for shouting out. Okay, here we go. What's the first thing we're going to do? Yeah, so I've got to say second, 7, second, clear work. Is everybody with me? Okay, now what do I put in for x01, Mr. Osawagwu?
0.137.
Very good. 0.137. Enter. Now what do I do? Arrow down. What do I do with this? Nothing, because I only have one series of data. Arrow down again. What do I put here? Very good, thank you. Enter. Arrow down. What do I do here? Is where? What do I do here?
Sorry, I was working ahead.
Oh!
I was just making sure I
Okay.
could get my own.
Well,
Press
take-
arrow down.
There you go. Now, what about x03? What do I do?
Asking enter port 4514.
0.4514. Enter. Arrow down. Ms. Volkova, what do we do here? Arrow down, very good. Ms. Wabi, what do I put here?
Negative 0.0888.
Yeah, but I can't put the negative first. I have to put 0.0888, and then hit the negative, and then what do I do? I got to hit enter. Okay, now check your work. Arrow up. Make sure you've got all that stuff in there. What's the next thing I do? Second, and then stat, which is above the 8 key. So now I'm going to arrow down. N is 4. What does the asterisk mean? Yeah, this is something that they computed. And to get the S sub, or the X bar, there we go. What's X bar represent?
Arithmetic mean.
Arithmetic mean. Very good. What's another name for arithmetic mean? Like your mom might say? Average, right? Arrow down. Like when my mom would tell me, you're just average.
My mom's never said that to me.
Your mom's never said that to you? Good. What, she said to you, you're below average? Oh, very good. By the way, raise your hand if your parents told you you were above average.
No.
No, go ahead, please. Please be. Ms. Wabi, did your parents tell you you're
Above average?
above average, right? Okay, now here's what I want to point out. How many people raise their hand when I ask if they ask, oh, you can push your hand down now. Right, the majority of the class. How is that possible?
Or an MBA student.
Oh, okay, well, we can do that. Well, let me throw one more out to you. When you ask Americans if they are a better than average driver or a worse than average driver, the overwhelming majority say,
Above average.
yeah.
Not possible.
No, not possible.
My husband would say no to that for me.
Okay, yeah, we're not asking for other people, right?
But my husband is also a professional driver, so.
Yeah. So I've never mind. Okay, back to the story. Let me put it this way. I love that radar cruise control because it keeps the driver from getting too close to the semi-truck in front of us. It's useful. Okay, back to the story. What were we talking about? Oh, S of X. This is, what is this?
Sample standard.
Sample standard deviation. And how would I get the variance from here? Square it. Okay, now for those of you who wanted to see it again, did you get it this time? Okay, go home, practice it again, watch the video. Sometimes these things slip away from people after they leave the room. Okay, so now we're going to move on to something called the normal distribution, and I've been telling you a little bit about it. We can generate this entire distribution using the mean and the standard deviation. And what this distribution represents is the probability of different outcomes. The probability of different outcomes. Every single possible outcome is underneath this bell curve. And so what is the probability that's represented underneath the bell curve? Yeah, it's 100% or 1.0. Now, this thing, the mean, is right there at the middle. You can think of the mean being the tent pole at the center of the tent. And then we can look at standard deviations, number of standard deviations away on either side, and they tell us some pretty interesting things. For instance, if I look at the mean from -1 standard deviation below the mean to +1 standard deviation above the mean, I have 68.26% of all observations that fall in that area. By the way, ignore the returns for now, because a lot of people get confused and think this only applies to stocks. No, this applies to all sorts of amazing stuff, and I'll tell you an example here in a minute. Okay, now if I look plus or minus 2 standard deviations, between those two things, 95.44% of all observations, 95.44% of all observations. And if I look plus or minus 3 standard deviations, now I've got 99.74% of all observations between those two things. Now, oftentimes we use, in fact, homework exam, I would tell you to use the approximations. By the way, I'm a lousy artist. Let's see here. So, here's your mean. Let's call that X bar. And then +1 standard deviation, +2 standard deviation, +3 standard deviation. They're supposed to be X's, by the way. And then over here, we're going to have -1 standard deviation, -2 standard deviations, and -3 standard deviations. Notice I'm using sample standard deviation there. What are they using on the picture?
Population.
Yeah, they're using the population standard deviation. Don't let that freak you out. I want you guys to be bilingual and understand the Greek and the English, right? The English is always the sample and the Greek is always the population. Okay. Now, for purposes of our stuff here, what I want you to know is between plus or minus 1, let's call that 99, or no, sorry, I was going with 3 first. Yeah, so 68%. 68% between those two. Now, if I go up plus or minus 2, I'm looking at 95%. And so far, I have not violated any of the rules of rounding, have I? No. Okay, now, down at the bottom, 99.74%. What does that round to, nearest percentage? Should be 100, but instead, what we say is 99%. Now, the reason that we say that is because, first of all, we know that there's still more stuff out here in the tails, and if we didn't go with 99%, then there would be nothing for you to talk about and calculate when I ask you about plus or minus 3 standard deviations. So don't let that freak you out. Okay, now another thing I'm going to tell you about the normal distribution is that it is symmetric about the mean. What does that mean? What does symmetric mean? Yeah, it's supposed to be the same on each side. And so that can start to tell us some things. For instance, we have 68.26% between -1 and +1. What does that mean is outside of plus or minus 1 standard deviation?
The rest of the.
Yeah, so we got 100% minus 68.26% gives us, well, let's use the approximation here. 32%. Now, that 32% is evenly divided by those two tails. You see what we're calling tails? So what does that mean is in each of those tails? 16%. And what if we're talking about plus or minus 2 standard deviations? We've got 95% of the observations between plus or minus 2 standard deviations. So when we look outside of that, how much do we have left over? 5%. So how much is in each tail? 2.5%. And finally, plus or minus 3 standard deviations, we've got 100% minus 99% gives us 1%. How much is in each tail? Yeah, half. And so you may see, and I will never give you 2 multiple choice answers, one of which was found with the approximation and one of which was found with the exact. And so for instance, if you're using the exact and you end up with 0.13% in a tail, and the only answer is 0.25%, what do you assume about the person that did the solution? They were using the approximation. Does that make sense? So don't let that freak you out. By the way, the instructions on all my exams, what did it say at the very beginning? Choose the what? Choose the best, right? So it's going to be, there isn't going to be one that's closer than. So regardless of how you do this on a multiple choice exam, you will be just fine. Okay, now the next question is this. Should this be on your note sheet? Yeah. Okay, so I was teaching China EMBA, and one of the people in the class was a Mongolian lady. Now, if you're not familiar with Mongolia, so you heard of Genghis Khan and Kublai Khan, they had a huge empire. They're very tough, stubborn kind of people. And she would tell you that. She would tell you that. Am I wrong? Never mind. Okay, back to the story. She calls me up to her desk during the exam, and I trot up there, and she says, "You did not give me enough information to solve this problem." Because I had given her a sample of data, and I was asking her probability questions. So all she had to do was plug that into her computer or her calculator, get the mean, the standard deviation, and now using the normal distribution, she can answer the question. She says, "You didn't give me enough information." And so I tap on her note sheet and I say, "Yes, I did." And she says, "No, you didn't." And I say, "Yes, I did." And I tap on this thing like twice. And then she says, "No, you didn't." And then I see her hands coming toward my lapels. What? Oh, yeah. And so I quickly jumped backwards, or she would have pulled me over the desk. She's a very strong woman. Anyway, and by the way, we are still friends on WeChat. So, okay, so back to the story. Why do I tell you that? I want to drive it home that this thing needs to be on your note sheet. And whenever you start to hear questions about what percentage of returns are above or below this, or what's the probability of, whoo, think about this thing, because that's where we're headed with that. And if you don't have this on your note sheet and you can't remember that, you will be lost. Questions? Okay, now let's move on and talk about another example other than stock returns where the math is easy and you guys hopefully are all familiar. What is IQ? What does it stand for?
Intelligence.
Intelligence quotient. And what does it theoretically measure? How smart you are, right? Like your raw horsepower, not how much education you've had, just your raw horsepower. Okay, now, what do you think the average IQ is by design? Oh no, we'll get to 70 in a minute.
What's the scale?
What's the scale? That's what I'm asking, right?
So it's like 0 to like 160.
Oh, okay. So, it actually, because it's normally distributed, it has no limit on the other end, right?
So it's infinite.
Yeah, it could be. Could be, right? Okay, back to the story. Average IQ by design, 100. Average by you should have yelled that out.
Somebody to give other chance.
He's obviously above average or he would not have known that, right? Okay, so average is 100. Most people, used to people knew that. But the thing they don't know is that the standard deviation of intelligence is 15. The standard deviation of intelligence is 15. So, knowing these two things, now I can generate the entire normal distribution. What number is going to be at that tent pole position? 100. And then over to the left, I've got the mean minus one standard deviation. What's that number going to be? 85. Mean plus one standard deviation is going to be how much? 115. So here's what I could ask you. What probability, what proportion of people on the planet have an IQ between 85 and 115? And your answer would be 68%, right? Now, what if I go down to minus 2 standard deviations up to 2 plus 2? Down at the bottom, what's 100 minus 30? 70. And then 100 plus 30, this one's easier for most people, it's 130, right? So between 70 and 130, what do we have? 95%. And if I go between 55 and 145, what do I get? 99% or 99.74%. Okay, now in fact, this idea of standard deviations is so important for measuring cognitive ability that they actually, in the beginning, named these different levels, different things based on standard deviations. So, I'm going to go through these. Some of these are now considered offensive. So keep in mind that I am a 200-year-old Frenchman when I say this, right? Because some of these things are now considered bad words. But plus 3 standard deviation, 145, what do you think that we would call that? Genius, very good. Genius, plus 3 standard deviations. Plus 2 standard deviations, I believe they called gifted, I'm not sure. Plus 1 standard deviation, don't know the name. Minus 1 standard deviation, don't know the name. Minus 2 standard deviation, we say these people are mentally, and it starts with an R. Do you guys know this word? I try not to use it out loud, right? But you guys know. Okay, and then I can't remember whether the bottom one was moron or idiot, but it gets really offensive, of course, on the left-hand side, right? But my point to you isn't that you should go around using those terms. My point to you is that is how we are categorizing this kind of thing. Now, I could ask you some other questions. Now, so far I've softballed it by just asking you what's between this and that. What if I ask you what percentage of people have an IQ above 115? Let's talk about how to do the calculation. So we're going to calculate something, and it's actually, the accurate is t, but you might have also heard of it as z for the population stuff. But we're going to look at it, and we're going to say whatever number we are talking about, we're going to subtract the mean and then divide by the sample standard deviation. So when I ask you a question about 115, you're going to try to figure out this is how many standard deviations, number of standard deviations away from the mean. Okay, so we've got 115. What's the mean? 100. And what's the sample standard deviation? 15. And so my t would be plus 1. That tells me we are looking right here. I'm looking to the right. One. Now, what if it had been negative? Been on the other side, right? Okay. Now, what do we do with that information? Well, I could ask you what percentage of people have an IQ higher than 115, and now what would your next step be?
I would deduct anything below that with 100%.
Okay. So what is below it?
68 and everything down.
And everything down. Oh, he's being very clever. Can you give me a number?
So it'd be 16%.
No, because that would give you 2 tails, right?
Yeah, divided by 2.
Yeah, we have to divide by 2. So there's 2 ways to get after this. Number 1, we can take 100% minus 68. Oh, crap. Minus 68.26%. Oh, you jerk. I've been complaining about this for years, and do you know how often it gets fixed? Okay, here we go. Okay, so the first thing you're going to do is 100 minus 68 and then divide by 2. And that would give us 16, right? Or if you use the exact, it'd be 15.87%. Either way. Back to the story. How is the other, what's the other way? Well, there are 2 things that I know. I know that this thing is symmetric about the mean. And I also know that there is 100% underneath it. And so if I ask you what percentage of observations will be at mean or below, what would your answer be? 50%, right? And so I could take 50% to represent the left portion, and then I could take, because this is symmetric, I could just divide 68.26 by 2 and get the 34%, add those together and get 84% below, subtract from 100 gives me 16 above. There is 2 ways to do every single one of these calculations. As long as you get the right answer. Do you think I care how you do it? Absolutely. Whatever, absolutely not. Whatever works for you, go for it. Okay, so we just figured out that 16% are above 115. What if I ask you what percentage of people are above 130? Well, we would start like this. 130 minus 100 divided by 15 is equal to what? Positive 2, right? Okay. So, how would I go about this one? Okay, so we go 100 minus 95, divide by 2 would give us 2.5%. The other way I could do it is to take 95 divided by 2, which gives me what, 47.5, and add 50% to it, which gives me 97.5, subtract from 1 gives me 2.5%. Now, every one of these things is going to have, depending on which side of this it's on, is going to let you know whether or not it would be easy to go one way or the other. My encouragement to you is learn one way and get good at it. Okay. Now, let's ask this question. What is the probability that someone's IQ is lower than 55?
That's
Yeah, so we're gonna say it's 55 minus 100 is equal to negative 45 over 15 is minus 3. See how that works? Okay, and so we know plus or minus 3, let's say it's 99%. And so we have 1% left in the tail, so how much is in this tail right here? Yeah, 0.5%. What if I ask you, what are the chances that someone's IQ is higher than 70? How would you go about that? So first of all, are you sure it's negative 1?
Oh wait, sorry, 70 is 2.
Yep, minus 2. Okay, so we know we're 2 standard deviations below the mean, and I'm asking you, what's the probability that their IQ is higher than that? Yeah, we're going to go, the part that we're looking for, watch the cursor, the part that we're looking for is all this stuff over here. The only part that we're excluding is over here. If I know, for instance, that this tail is 2.5%, and how did I get that? 100 minus 95 divided by 2, right? So I know this tail is 2.5%, and I'm interested in everything but that tail. What can I do? Yeah, 100 minus 2.5 gives me 97.5%. Okay, let's put this in a real world kind of situation for you. Assume that you have just taken an IQ test and your IQ is 145. Do you feel good about yourself?
Yeah.
Yeah, what are we going to call you? Genius. And not in that sarcastic way that my sister calls me a genius, right? We're really going to mean it. Okay, so you're a genius, and let's find out what percentage of people, and this time we'll use the exact, what percentage of people are smarter than you? Well, we know that 145 minus 100 divided by 15 is equal to what?
3.
Yeah, plus 3. Okay, so we know that we are out here plus 3. What percentage of people are between minus 3 and plus 3? 99.74%. So how much does that leave out in the tails? 0.26. 0.26. Now we're going to, how are we going to figure out what's in that upper tail then? Divide by 2, so we end up with 0.13%. Now, let me ask you this question. Are you still feeling good about yourself? Yeah, man, only 0.13% of people are smarter than I am. Let's get your calculator out. And we're going to give you some disturbing news. So here's what I want to do. I want to put in 0.0013. That is the decimal equivalent of 0.13%. And then I'm going to multiply by 8, followed by 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. Why are we doing 8 billion? That's the population of the planet. Now, do you think we've actually counted that? No, it's kind of rough, but we get it. I'm going to say equal to. Check that out. This is the number of people who are smarter than you, 10.4 million people. Now, I have some, and right now you're feeling kind of bad, but I've got some good news for you. At least a portion of those people are out in the middle of nowhere, where they have no power, no internet, probably no school. And so you're probably not going to have to compete with them. But the rest of those people are definitely your competition. What's that? Yeah. Now the good news is that here in this country we have lots of opportunities, right? So you can still find a place, no matter where you're at on the spectrum, you can still find a place. Questions? Okay, now let's take this to returns. And for large stocks, on the chart we had earlier, the mean was 11.8%. So that's what we're going to put right in the middle. And then, can anyone tell me what the standard deviation is just looking at this chart? How would you find how much one standard deviation is just looking at this chart?
20.5%.
20.5. How did you get that?
32.3 minus 11.8.
Yeah. So she started out saying, well, I know the plus one standard deviation is 32.3. I'm going to subtract 11.8 and get 20.5. I can check her work by taking 11.8 minus 20.5. What do I get? Minus 8.7%. So here's how the problems would be worded. What's the probability that you get a return between minus 8.7% and 32.3%? The probability is what? 58%. What is the probability I would get a return between minus 29.2% and 52.8%? How much? 95. Very good. And then what is the probability I would get a return between minus 49.7 and plus 73.3%? 99.74, right? Okay, so now let's talk about one reason that we know the stock returns are not truly normally distributed. What is the lowest a stock return can ever be? Oh, I wish it were 0, right? My portfolio has actually shrunk over the last 6 months, which means my return was negative. Now, what is the lowest return you can possibly have then? Yeah, the amount you put in, which would be 100%, right? So minus 100%, we know stock prices can only go to 0. The reason they can only go to 0 is because of limited liability. And so the most you're ever going to lose on any given day is 100%. If everything just went to 0, boop, you've lost 100%. And so we say that over here on the left-hand side, this thing is truncated, which means it's just cut off. Truncated on the left-hand side at minus 100%. Okay, now let me tell you the other thing that we know about the distribution of stock returns. We say that this distribution for stock returns has fat tails. Fat tails. What do we mean by that? We mean that there are more observations way over here and way over here than there should be if this thing were perfectly normally distributed. And so, is this thing a perfect normal distribution? No. Could we even test whether or not it is? No, we don't have enough data. We already know that it's truncated. We don't have enough data to know whether those fat tails are just an outlier that'll work itself out over time. If you were to live another 10,000 years, you might have a good idea. I don't plan to be around that long. Okay. So, now let's go with some more difficult type things. What if I ask you, what is the probability that the stock will not lose more than 8.7%? What's the probability the stock will not lose more than 8.7%? So how many standard deviations below the mean am I? 1. And we're looking for not. And so what we need to do is find out what's in this tail over here and subtract from 100%. And so that's plus or minus 1 standard deviation, which means that it's 68% in the middle, which means 16% in each tail. What's 100 minus 16? 84%. And so there is an 84% chance that this stock will not lose more than 8.7%. Now, a lot of times students get freaked out because the way that question is worded, do you ever see a negative sign in it? No. How did I know to put the negative sign? Lose. When a stock loses a percentage, that is a minus, right? Okay, what if I ask you, what is the probability that a stock's return will not exceed 52.8%? Yeah, so we got to figure out what's, so 52.8% is plus 2 standard deviations. By the way, I could be doing the same thing here. 52.8 minus
11.
11.8 divide by 20.5. So I've got 31 or 41 divide by, oh wait a minute, is that 31? 52.8, you're right, it's 41. I don't know why, I just had a moment there. Okay, so 41 divided by 20.5, what is that? 2. So we know we're plus 2 standard deviations. We know that between plus and minus 2 is 95%. Therefore, how much is outside of that? 5%. How much is in each tail? 2.5%. And so how would we figure out the probability that it won't return more than 52.8? Mr. Holman.
One more time?
How will we determine the probability that this stock will not return more than 52.8%? He was obviously somewhere else.
Yeah.
We're going to skip you. Ms. Ware.
Subtract 95 and divide by 2.
Okay, so we've done that, and we know that there's 2.5% in that top tail. But what's the probability that it won't return more than 52.8%?
97.5.
And how did you get that?
Subtracting the 2.5
From?
100.
Yeah, because there's 100 under the whole thing, minus the 2.5. That gives you the 97.5. Are you back with us, Mr. Holman?
Yes.
Very good. Okay. Questions? Now, I guarantee you, you will not get this from just this lecture. So what you need to do is you can watch this lecture again, but I also have some examples out there on a video under Chapter 10, under videos, under examples. Go out there and watch how I do these calculations and do it again and again. Then jump into the practice, then do the homework. Questions? By the way, will they be giving you this information in the problem?
No.
No. Will they be giving you that information? No. On the exam, where are you going to get this information from? Your note sheet, unless you're just brilliant and you can remember these things. Let me assure you that even if you are brilliant, you'll forget during the exam. So go ahead, put it on your note sheet. Okay, now we're going to go and we're going to talk about a different kind of average or mean. So far, we've been talking about arithmetic average, and that's the one that you and your grandma share. That's just where you add everything up together and divide by the number of observations. And for arithmetic, it doesn't matter whether you use percentages or decimals, it's going to work out either way. If you throw percentages into this thing, you're going to get percentage out. If you throw decimals into this thing, you're going to get a decimal out. It's all good. The geometric average is a little more tricky. First of all, it's new to most students. Secondly, it's a little more tricky on the math side. And third, this one's important, write this down. You must always use decimal returns. You must always use decimal returns. You must always use decimal returns to find geometric average return. You must always use decimal returns to find geometric average return. So we're going to do a simple example here. So we have a portfolio, and at time 0, the value is 100. At time 1, the value is 50. At time 2, the value is 75. And so we are going to figure out return for each of one of these. So you cannot find a return for time 0. Can anyone tell me why? Yeah, you got to have the t minus 1, right? You got to have the thing that came before to be able to do this. So we can start here figuring returns. And how am I going to do that? T plus 1 minus t divide by t. right? So it's the value at time t minus, or t plus 1, minus the value at time t, divided by the value at time t. So 50 minus 100 is how much? Negative 50. Negative 50 divided by 100 is how much? It's minus 50%, or minus 0.5. Does that make sense so far? Okay, now to find the return from time 2, at time 2, what we're going to do is take 75, which is our new value, minus the previous value, which is 50. Now we're down, so 75 minus 50 is 25. What's 25 divided by 50? It's half, right? So 0.5. And that's plus, just in case you missed that. Now, my question to you is, and keep in mind, we're not talking about this, what's the average return for this stock over that period? It's 0, right? If you add those things together, divide by 2, you're going to get 0. Now, does it make sense, though, that this is 0? Because after all, we started off with 100, and we ended up with 75. No. So the problem with this arithmetic average is that it is ignoring compounding. It's ignoring compounding. I remember the financial crisis, the S&P 500, let's say it was down 30% from its peak. And then I remember like some years later, I saw this lady on CNBC, she's one of the talking heads, and she said, well, the S&P 500 was down 30%, and now it's up 30%, so we're right back where we started. Was she right? Absolutely not. Let's walk through this with some real numbers. If the S&P 500 started at 100 and then went down by 30%, what would it be at now? 70, right? Now, if it goes from 70 and goes up 30%, what's 30% of 70? 21. And so now I add 70 plus 21, I get how much? 91. I'm still down 9% from the high. Does that make sense? So that's the problem with with arithmetic average. Now, don't get me wrong. Arithmetic average is still quite important. It does answer questions for us, and whenever we make statistical calculations, we always use arithmetic average. For instance, when we're doing the normal distribution, it's always the arithmetic average. Now, let's talk about the geometric average. Remember the geometric average, let's go back up and look at the formula one more time. What we're going to do is take 1 plus the return, and we're going to do that for all of them. And we're going to multiply all those together, and we could have, let's say, n of them. So if n is 5, we're looking at, there would be 5 of these 1 plus r terms. Multiply them all together, and then we're going to take it to the 1 over n power. If n is 5, we're taking it to the 1 over 5 power. And then we're going to subtract 1. Now, why are we subtracting 1? Remember how we added 1 to everything before? Now we're going to subtract 1 to get back to a raw decimal percentage, or a raw decimal. Okay, so that is how we're going to get geometric average. So now let's talk about how we're going to do this. 1 plus R1, well, R1 is minus 0.5. 1 plus R1 is just 0.5. Does that make sense? 1 plus negative 0.5. And then the second one is 1 plus R. So what's 1 plus 0.5? 1.5. So now I've got basically 0.5 times 1.5. What's 0.5 times 1.5? 0.75. Now, what is n in our calculation? 2. It's going to be 2. Now, some of you may already know that 1 over 2 to the 1/2 power is just square root. And so you're like, aha, I got a square root button. What if it's something larger than that? I'm going to walk through how we do that. So here we go. Get your calculator out. So I'm going to say, if you want to do this whole thing in your calculator, here's what I would do. 1 minus 0.5 equal times, open parentheses, 1 plus 0.5, close parentheses, equal. That gives us the 0.75. And then I'm going to go up here. Do you see this key above the 9? It says y to the x. I'm going to hit that button. And then I'm going to say open parentheses, 1 divided by 2, close parentheses, equal. And that's going to give me this number here. Now there's one more step that I need to do before I can find return. I have to subtract 1. I have to subtract 1. And that's going to give me minus 13.397 something percent. Now, does that look a whole lot more reasonable than 0? Yeah, if we're going from 100 down to 75 over 2 years, it means I'm losing 25 over 2 years. I could approximate and say, yeah, we're losing about 12.5% a year. This number makes a whole lot more sense because it takes compounding into effect. And so let's do one more thing here. Let's verify this on the calculator. By the way, the calculator takes compounding into effect. So here's what I'm going to do. I'm going to say second clear TVM. Oh, I'm going to store this thing. Actually, I'm going to multiply by 100 and store 1 because we're going to have some fun with that number here in a minute. Now, I'm going to say second clear TVM. We've got 2 years worth of data, 2n. We're starting off with 100, negative, present value, 75, future value. Why did I make those different signs? They're cash flows in opposite directions. It's the sign, what's it called? Yeah, it's the way the calculator works. For some reason that word's escaping me.
Convention.
Convention, thank you. It's a sign convention on the calculator. Okay, now what I can do is compute I per y. Does that number look familiar? Yeah. Minus, recall 1. We're going to see how much difference there is. There is no difference. So this is going to give you that same outcome because it takes compounding into effect. So what do each one of these? I told you they both have meaning. So let's talk about the questions that they answer first. The arithmetic average answers the question, what was your return in an average year over a particular period? And you can see that 0 would be the correct answer for that. The arithmetic mean does answer that question. What was your return in an average year over a particular period? Whereas geometric return, average return is what is your average compound return per year over a particular period. Now the next thing I'm going to tell you is that geometric average, let's do it this way. Arithmetic average is greater than or equal to geometric average. Now, how could it be equal to? What if we had no change whatsoever? So the standard deviation is 0. This thing is just constantly at the same return. That's the only time that you would have the arithmetic average and the geometric average being the same. And so let's say that this was 0.08, 0.08, 0.08, 0.08, 0.08. So that's 4 0.08s, right? So can anyone tell me what the arithmetic average would be? Oh, come on, Ms. Wallaby. 0.08, right? You didn't even have to use your calculator, I hope, for that. But let's go and look at the geometric average. First thing I'm going to do is say 1.08 times 1.08 times 1.08 times 1.08. Now I'm going to take that to the 1 over the n power. What is n? 4. So I'm going to have y to the x, open parentheses, 1 divided by 4, close parentheses, equals. I'm getting 1.08. What's the final step? Minus 1. It's only when the return is the same throughout, that the standard deviation is 0, so the return's always the same. In that case, the arithmetic average will be equal to the geometric average. Now, what if there were some change here? I'm going to put some numbers in here, and hopefully we can all agree that they still have an arithmetic average of 8. So I'm going to do 6%, 10%, 6%, 10%. Can we still all agree that the arithmetic average is 8? Okay, so here's what I'm going to do. 1.06 times 1.10 times 1.06 times 1.10 equals. And now I'm going to say y to the x, open parentheses, 1, divide by 4, close parentheses, equal minus 1. You see that we now have something less than the arithmetic average. And so your geometric average is always going to be less than or equal to. As that standard deviation grows, your geometric average will fall further away from arithmetic average. Okay, so that answers the first part of this. Now, it says the geometric or the arithmetic is probably too high for longer periods and it's probably too low for shorter periods. So we know that geometric average is typically lower and arithmetic average is typically higher. So that handles the first part of that. The second, having to do with the duration of the period, is rather complex. And if you just have a burning desire to know why that is, I have posted an academic paper on the Chapter 10 folder, and you guys can go out there and take a look at it. Do you know what my expectation of how many of you will actually do that is? Below average, very good. So less than half of you. I would say, so economists, raise your hands. Yeah, maybe you guys. Maybe. Maybe. You skimmed it. Whoa, she's ahead of the game. Very good.
Did you write the paper?
What's that?
Did you write the paper?
No, of course not. I try not to assign anything to you that I actually wrote because I know the idiot that wrote it, right? Okay, questions?
About like 3/4 of it, and I kind of got bored, so I just skipped the rest of it.
Yeah. Okay, so let's talk about how you should read an academic paper. The first thing you should do is read the abstract. What's an abstract?
Like the summary.
Yeah, it's a summary of the whole thing. If you read the abstract and you say, well, that's boring or stupid, what do? You don't read anymore, right? Let's say that you look at the abstract and you say, ooh, I'm intrigued. What do you do next? Read the introduction. If you are still interested, then you could go read the conclusions. And if you are still interested, you could go read the results where they walk through what they actually did. Now, that is the way that people who think in terms of language do it. People who think in terms of mathematics will read the abstract and then they'll go straight to the tables. And then they'll start asking questions like, well, what is this variable? And I'm like, well, if you'd read the paper, you would know, right? And so I actually prefer to go about it the verbal way and then look at the tables to make sure they're not lying about what their results really are. Now, so typically, do people actually read entire academic papers? Rarely. In fact, when I submit them to referees to try to get them published, oftentimes they'll say, you know, this would be a so much better paper if you did this, this, and this. And I'm like, well, I already did this, this, and this. You obviously didn't read the paper, you jackass, right? Okay. Unfortunately, it's a blind review process, so I don't get to actually know who these people are. I don't know, maybe that's for the better.